Now, for our investigation problem. In our investigation problem, we have rectangles. The perimeter, for the first set of rectangles that we have, the perimeters are equal to 24 units. And we need to draw our first rectangle, which is rectangle B, with area 27 square units and perimeter 24 units. A is the one that is given to us. It has length 10 units with 2 units and the area 20 units squared. So, no difficulty. 10 multiplied by 2 is 20. And in order to find the perimeter, we can add 10 to 2, then another 10 with another 2, and that will give us 24. Or we can use 2 times the length plus width, 2 times the sum of the length and the width. So we'll have 2 times the sum of 10 and 2, and that will give us 10 plus 2 is 12. Multiply that by 2, that's 24. B is of area 27 units squared, and the perimeter is the same. If the perimeter is the same, that means when we add all of the sides, we need to get 24. And we will take a look at the implication of this on subsequent slides. In order to get 27 units squared, we say 9 multiplied by 3 is 27, and then we say 9 plus 3 plus 9 plus 3 is 24. Or we can use the formula for area that we'll take a second look at in a short while. C as area 32 units and the perimeter 24 units. All of the perimeters for the first set of rectangles will be equal to 24 units. So we have 32 units squared, and we are sure that the length is 8, the width is 4, the perimeter is 24. How can we be sure that if we have an area of 32 units squared, that the length is 8 and the width is 4? That we'll take a look at in a short while. Now, this is a scenario that we have right here where the perimeter is 24 and D is the largest rectangle with that particular perimeter. We will show that the length is equal to the width is equal to 6, because as a matter of fact, if we are taking a look at a particular perimeter, then the rectangle with the largest area for that particular perimeter will actually be a square. So the length and the width must be equal. The examiners are taking us out of the box or out of the rectangle a bit by saying what? We have a rectangle with perimeter 36. What is the largest area that we can have for that particular triangle? And what is the value of length and width that might be responsible for that largest area? Well, the largest area that we have will be the area of the associated square. The length and the width are equal, and they are equal to 9 units. If the length and width are equal to 9 units, then the area will be 9 multiplied by 9, or 9 squared, and that is equal to 81. Each problem should take on average about 15 minutes to complete. However, one key factor that could cause candidates to take about 7 minutes to complete this one is the consideration of the semi-perimeter. The perimeter is 2 times the sum of the length and the width, as we have it right there. Half of the perimeter, which is the semi-perimeter, is the length plus the width. All rectangles in the first set have a perimeter of 24 units. The sum of the length and the width of each has to be 12 units. So if we reflect to the other slide, half of the perimeter is 12. Therefore, any length and width that we are using must have a sum of 12. See, 10 plus 2 is 12, 9 plus 3 is 12, 8 plus 4 is 12, 6 plus 6 is 12. But this one is different. This one does not have a perimeter of 24 units. Right, so we are considering the semi-perimeter. All rectangles in the first set have a perimeter of 24 units. The sum of the length and width of each has to be 12 units. There we have a table. And finally, 8 plus 4 is equal to 12. Right. Any other rectangle that we will choose with a perimeter of 24 units, the sum of its length and width has to be 12 units. Also, as the value of the length and the width gets close to each other, the value of the area increases. Notice that we have 10, 2. Area is 20. 9, 3. The area is 27. 8, 4. The area is 32. So as the length and the width are approaching each other, the value of the area is increasing. Then if as they get closer to each other, the value of the area is increasing, when will they actually produce the largest area? Of course, when they are equal to each other. That is when we'll have the largest value of the area. If such be the case, the maximum area will be obtained when the length and width are equal. Two numbers with sum is equal to 12, and they are equal because the semi-perimeter is 12. That means the two sides of the rectangle, when we add them, we get 12. So the sum is 12, and they are equal. If they have a sum of 12 and they are equal, both of them must be equal to 6. Before the end of the day, the examiners attempted to determine if our answers were only based on trial and error, or if there is some logical reason behind our deductions. And that is why they gave us another rectangle that had perimeter 36 units and asked us to find the maximum area of such rectangle. Remembering from the previous slide that the sum of the length and width is always half of the perimeter, the sum of the length and width is therefore what? Half of the perimeter, half of 36 is equal to 18. Do not forget that what? The sum of the length and the width is half of the perimeter. Another principle that we need to be aware of is that for the maximum area, the length and the width have to be equal. So the length and the width must be equal. If they are equal and their sum is 18, the value of each one will be 18 divided by 2, which is equal to 9. Now, based on the calculations on this slide, we may make a further deduction. Notice that we started off with the perimeter divide by 2 in order to arrive at the sum of the length and width. Finish up by dividing by 2 again in order to arrive at the length of each side of the square. So we get the sum of the length and width by dividing by 2. Then we finish up dividing by 2 again in order to arrive at the length of each side of the square. Dividing by 2, then dividing by 2 again is effectively dividing by 4. These are our two conclusions. The first one, given a particular perimeter, the rectangle with the greatest area will be a square. And 2, each side of the square is a quarter of the perimeter. And those are our two deductions. Number 9. Function f of x is equal to 2x minus 7 over x. In order to find f of 5, which is what is required, substitute 5 in the place of x in the function f. So in the function f, everywhere that we have an occurrence of x, we replace that with a 5. Two times 5 is 10, minus 7 is 3. The result is 3/5. There we have our f of x, and we need to find the inverse. One suggested method is, in finding f inverse, we will take an expression of the function and replace x with f of x and f of x with x. So where we see x, we put f of x. Where we see x, we put f of x. Where we see f of x, we put x. So we have x is equal to 2 times f of x minus 7 over f of x. But what do we know? Our intention is to find f inverse, and we imagine that as soon as we finish this, then the expression so formed will be the inverse of f. And if such be the case, it is more appropriate to replace x with f inverse of x. Then we may transpose in order that we may find an expression for f inverse of x. We are dividing by f inverse of x on the right hand side. We usually flatten an expression if we are transposing formulae. We flatten the expression as a first step, and that is always a very good first step, by multiplying by the denominator. So we'll have x being multiplied by f inverse of x on that left hand side. Now we have two occurrences of f inverse x, one on the left and one on the right. We will just place them on the same side, preferably the right hand side. So we have 2f inverse x, this one is transposed over on this side, be a minus x times f inverse x. This negative 7 will be transposed to the left hand side. Now that we have two occurrences of f inverse x, to make f inverse of x the subject of the formula, we need only one occurrence. We will achieve one occurrence by factorization, taking a common factor of f inverse x. So 7 is equal to f inverse x, and we have the other factor will be 2 minus x. In order to find f inverse of x, we need to eliminate this 2 minus x that is multiplying it on the right hand side. We will therefore divide by 2 minus x. 2 minus x will be eliminated from the right hand side. On the left hand side, we have 7 divided by 2 minus x. Is that correct? I think that would want to write that expression with the f inverse of x on the left hand side. Like so. So f inverse of x is equal to 7 divided by 2 minus x. Look at this. Another more awkward form of the answer may be this one. Why is it called awkward? And why I am also including it? It is only called awkward because we have more negative terms than positive terms. And it is more appropriate if we can write our expression with the smallest possible number of negative terms. And why are we showing this one? Because some students will actually arrive at this expression in the examination or in practice. And because in Richard James Mathematics Resources you see this one, you are thinking that this one is wrong. They are actually equal. As a matter of fact, if you multiply the numerator and the denominator of this one by a negative 1, we will arrive at that one. Do not forget that multiplying both numerator and the denominator by the same number does not change the value, just the appearance of the number or expression. What do we imagine for this section? What do we need? I'm thinking that we probably need an expression for g of f of x. G is required to operate on f. If it is g of f of x, g is operating on f. We will substitute f in the function g. So there's our function g. Now we will substitute f into that function. Right. So we have g of x is equal to x plus 3. G of f is the square root of f plus 3. After doing that, we will replace f with its algebraic expression. So now, take this f, and in place of it, we have the algebraic expression for f, which is this one, 2x minus 7 over x. Then we attempt to simplify that expression that is under the square root sign. This is a method that you will see throughout Richard James Mathematics Resources. I have already created the slides for 10, 11, and 12. And throughout these practice paper solutions, I have added fractions to whole numbers by writing the whole number as a fraction with the same denominator as the fraction that we have. So the denominator that we have here is x. So we will create a fraction for this one with the denominator is x. So use the method of adding a fraction to a whole number in which we multiply the whole number by the denominator of the fraction and place it over the denominator, causing them to have the same denominator. Let us do that. So here we have 2x minus 7 over x. What do we have here? 3x over x. But if we cancel this, it is the same as 3. so we are sure that it is equal to 3. But it has the same denominator as the fraction that we have here. It therefore can be easily added to that fraction. Now that the fractions have the same denominator, they may be added by simply adding the numerator. In the numerator, we have common terms or like terms, and they will be combined. The 2x and the positive 3x, that's 5x. So we have g of f of x is equal to the square root of all of 5x minus 7 over x. We have 1 minus 6x minus x squared, and according to the instruction, we need to write that in a particular form. And we are sure that when we get that particular form on the CSEC CSEC examination, what is required is completion of the square. So let us complete the square on that expression. It is not impossible to complete the square on the expression as it is. However, let us rewrite it in the form that we are accustomed to by putting the x squared as the first term. In completing the square, we need to be aware that a perfect square cannot be negative. We need to remove the negative coefficient of x squared by factorization. The other term will be affected, which is the middle term here will be affected. So take a negative 1 or just the negative sign outside. Negative into negative is positive. If we are factorizing by a common factor, we need to divide each term by the common factor. Negative into negative is positive, and negative into negative again is positive. And then no doubt plus 1 also. The square will be completed by taking half of the middle coefficient, and the middle coefficient is 6. Taking half of 6 and squaring it. By so doing, we have introduced 9. That was not there before. Let's put that up there. We have introduced the 9 that was not there before. We therefore need to compensate for it. That means, since the 9 was not there before, this expression, by including it, is different from the one that we have here. However, it is contained, the 9 is contained inside of the bracket that is multiplied by a negative 1. Effectively, we have introduced a negative 9. Therefore, to compensate for that, we need to add 9 to the expression. And that is what we have done right here. In writing the perfect square equivalent of this trinomial, we need to be aware that the number or expression or term that we square in order to get x squared is x. And what did we square to give 9? 3. As a matter of fact, if we square a negative 3, we will get 9. And if we square a positive 3, we will get 9. But this term that we have here is positive. We are therefore sure that it is a positive 3 that was squared. So we have x plus 3 all squared plus, of course, 9 plus 1 is 10. And the form that we have required that the positive 1, or we may say that the negative expression be placed second and the positive 1 first. So we have 10 minus x plus 3 all squared. We need to make use of the completed square in stating, because the statement of the problem said, hence state the maximum value of 1 minus 6x minus x squared. State the maximum value. The maximum value is the constant value. So the maximum is equal to 10. State the equation of the axis of symmetry of the quadratic function. The equation of the axis of symmetry is what we are after right now. Next, we need to state the equation of the axis of symmetry. As soon as some students see axis of symmetry, they write down x is equal to minus b over 2a. That is the equation or the formula for the axis of symmetry. And they will go straight ahead, make their substitution, and make their calculations. The problem said state. Therefore, we are sure that there must be some way to just look at the expression so formed and write down the equation of the axis of symmetry. State means that we should be able to look at the expression and write down the answer. The maximum occurs when the expression inside of the brackets is equal to 0. That is, x plus 3 is equal to 0. If x plus 3 is equal to 0, this simple equation will yield x is equal to negative 3. What do we add right here with 3, and the result is 0? A negative 3 will do it. X is equal to negative 3. And that is our equation of the axis of symmetry. X is equal to 3 is the equation of the axis of symmetry. And it is also the value of x at which the maximum occurs. When solving a mathematical problem, it is not always sufficient to supply a correct answer. In so doing, it is necessary to answer exactly what was asked. Therefore, when answering a question, it is not only important to just give the correct answer. Give the answer in the way that it was solicited from you. Finally, for this part of the problem, we need to solve that quadratic equation. The expression cannot be factorized, so we have two choices. One, use the quadratic formula, or we may solve by completing the square. Since we already have the completed square, let us use that method. Put our completed square right there. First, we will transpose the negative portion of the expression to the right hand side in order to give a positive result. So don't keep on fiddling around with a lot of negative signs. Students may manipulate negative signs successfully, but a very good suggestion I'm making to you is that if you can eliminate the negatives immediately, go straight ahead, and that is what I am about to do right here. So this one is transposed. We will next eliminate the square from the right hand side. This results in the square root of 10 on the left hand side, and it is important for us to be aware that square roots always occur in pairs, a positive 1 and a negative 1, plus or minus the square root of 10. And we have x plus 3 right there. Need x to be alone? 3 remains and will be transposed to the right hand side. Of course, that is as a negative 3. So x is equal to negative 3 plus or minus the square root of 10, and the square root of 10 may be found, and it is found to be 3.162. Negative 3 plus 3.162 turns out to be 0.162, and negative 3 minus 3.162 turns out to be negative 6.162. The answer is required to be written correct to 2 decimal places. So write those answers correct to 2 decimal places. Take a closer look at that on the next slide. Write the given number correct to 2 decimal places. Locate the second decimal place beginning at the first digit to the right of the decimal point. That is your first decimal place, and there is your second place of decimal. Check the digit that is next in order of significance. That is the one immediately to the right. The digit is a 2, which is less than 5. For those that are 5 or more, we will add 1 to the digit in question. But in this particular case, it is a 2. It is less than 5. We therefore do not add 1 to 6. So 6 goes back as it is. The other digits are not affected. That is, those to the left are not affected and are included as they are. A place holding 0 is not necessary because it does not contribute to the number of required decimal places, nor contribute to the value of the number. So it does not contribute to the number, the value of the number, and it does not contribute to the number of decimal places required. Number 10, circle theorem. This is a problem for Atiyah Sutton or for Dwight Harrison. In the first part of this problem, we will find OGF. 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 This angle right here. OGF. Now we have a triangle. Triangle OGF is isosceles because OF and OG are radii of the circle. So this is an isosceles triangle. OFG and OGF are the two equal angles. Their sum is what remains of 180 degrees after subtracting 118 degrees. This being an isosceles triangle, these two angles are equal. All angles in a triangle add to give 180 degrees. Therefore, when we subtract this 118 degrees from 180, the remainder is to be shared equally between this angle and this one, because this triangle is isosceles. So OGF is equal to what remains after subtracting this angle from 180 degrees, and we divide the result by 2. So OGF is equal to 31 degrees, and so does OFG, 31 degrees. What is our next angle? DEF. DEF. What is significant about DEF? DEF is the angle that is opposite to DGF. DGF. It is opposite to DEF. Those are the angles. And they are present in a cyclic quadrilateral. We have them in a cyclic quadrilateral, and they are opposite to each other. Opposite angles of a cyclic quad add to give 180 degrees, or we say they are supplementary. However, of the angle DGF, only a part of it we have here, which is this one. This one is missing, and we need to determine this angle so that we can find all of this angle in order to find this one. So only a portion of DGF is known. We need to find the remainder, which is DGO, first, before we can take a look at the cyclic quad rule that we may use to find DEF. What do we know? A radius and a tangent meet at right angles. Therefore, this angle is 90, this one being 65. Radius and tangent meet at right angles. OG meets GHS at right angles. DGO is what remains of 90 degrees after subtracting 65 degrees. So 65 degrees is right here, and the entire angle is 90 degrees. So subtract 65 from 90, and we will arrive at the other angle, which is 25 degrees. So now that we have the entire angle right here, we may go straight ahead and use the cyclic quad and the supplementary angles that are opposite to each other in order to find the angle DEF. The angle opposite to DEF in the cyclic quadrilateral is now known. Opposite angles of a cyclic quad are supplementary. DEF is what remains of 180 degrees after subtracting the sum of 31 degrees and 25 degrees. And what is that? 124 degrees. Usually, when CSEC gives us a problem that requires that we construct a diagram, the order in which the information is given is convenient for drawing the diagram. Right? But I've seen few and far apart situations in which we may not use this principle, but we may use it on this occasion. So we will draw our diagram. The bearing of K from J is 54 degrees. The bearing is taken from J. So it is the bearing of K from J. So the bearing is taken from J. If it is taken from J, that angle that represents the bearing must be at J. Also, bearing is taken clockwise beginning at north. The north line has to be at J. So the angle is at J, the north line is at J, and the bearing is 54 degrees. So we have north line at J, going in a clockwise direction 54 degrees. This is the line that we have for KJ. L is due east of K. Come on. East, no problem with that. JK is 122 kilometers and KL is 60 kilometers. No trigonometry without triangle. Complete the triangle. There is our completed triangle. What do we do next? According to what is required, we need to make some calculation. And the first one is the measure of the angle JKL. So let's begin our calculation of the angle JKL by inserting a north line at K. So there we have it. The north-south line is at K. Alternate angles that we call Z angles are equal. One portion of the angle JKL is 54 degrees. So, after inserting this north-south line, we are going to make use of what? Alternate angles. So let us make use of alternate angles. There we have alternate angles are equal. This being 54 degrees causes this to be 54 degrees, and the angle that we are attempting to find is JKL. JKL. A portion of that angle is missing, but that's not difficult. That is a right angle. The other portion is where east meets south and is therefore equal to 90 degrees, a right angle. East meets south. JKL is the sum of those two angles. So the angle JKL is equal to 90 plus 54, and that is equal to 144 degrees. 144 degrees. Any other calculation? Of course, we have just started. JL is what we need to find. This distance JL. The facts that we are about to use is that JL is opposite to a known angle, which is 144 degrees. And we have the two sides that form the angle. Finding JL is a candidate for the use of the cosine rule. We are using the cosine rule. It is always used when we have an angle and the two sides that form the angle, or we may say it this way: two sides of a triangle and the angle that the two sides form. It may be used to find the side that is opposite to the angle. That's a candidate for the cosine rule. And there we have an arithmetic expression of the cosine rule, in which we are saying JL squared is equal to the square of one side plus the square of the other side minus 2 times the product of one side and the other side. Then we multiply by cosine of the angle that the two sides form. in this series from 8 to 12 in Richard James Mathematics Resources, we will take closer and closer looks at the application of the cosine rule. So we have JL squared is equal to the square of one side plus the square of the other side minus 2 times one side times the other side multiplied by cosine of the angle that the two sides form. Square this number, square this one, then multiply this, we have it right here, and cosine of 144 is negative 0.809. The cosine of an obtuse angle is always negative. Therefore, when we are applying the cosine rule and we have an obtuse angle, we need to be mindful that the negative will multiply by the negative, resulting in a positive. Then the total sum is 30,342, which is JL squared. To find JL, we will find the square root of 30,342. That turns out to be 174.2 kilometers. In calculating the bearing of J from L, which is what we need to do next, we will make use of the internal angle of a triangle that is located at L. We are attempting to find the bearing of J from L. Therefore, the bearing of J is what we need as taken from L. The angle that represents the bearing must be located at L. We are taking it from L. The angle that represents the bearing is at L. But we cannot just jump and find the bearing without considering that we are within the confines of a triangle. Therefore, we need to use the triangle and find the size of the internal angle that is located at L. That is how we may be able to find any other angle that may be located at L. We have to use the one that is within the triangle at L in order that we may find the size of any other angle that may be located at L. And we are making use of the cosine rule. In this particular case, using the sine rule is safe because we are sure that this angle is acute. When we are not sure that an angle is acute, or we are sure that it is not acute, then the only safe method is by using the cosine rule. But we are sure that it is acute. Therefore, we may go straight ahead without any hesitation and use the sine rule. And the sine rule is pertaining to sides and angles that are opposite to each other. Finding the angle L, we say what? Sine of the angle L over the side that is opposite to L. And we have this side and the angle opposite to it. Sine of 144 degrees over 174. Right, so angle and side opposite, angle and side opposite to it. The only unknown here is L. Dividing by 122, we multiply by 122 on the right hand side. Then we may simplify this. We know that with the kind of scientific calculator that we have today, this is a matter of one single step. Sine of L is equal to 0.412. What is L? L is sine inverse of 0.412. Do not forget that if we have the sine, cosine, or tangent of an angle already, in order to find the angle, we go in the reverse order, taking the reverse sine or inverse sine or sine inverse, or if it is cosine or tangent. So L is equal to sine inverse of 0.412, 24 degrees. Now we may make an attempt of finding the bearing of J from L. The bearing is located at L. No bearing without north, so we have to have a north line. The bearing is measured in a clockwise direction beginning at north. Let us show the bearing of J from L. We have to have a north line at L, and the bearing will go in a clockwise direction beginning at north. The bearing is short of 3/4 of a revolution, and 3/4 of a revolution is 270 degrees, and it is short. Notice that we are going here. We are right here. We stop there. 270 degrees is right here, which is 3/4 of a revolution. We are short of that by 24 degrees. We are short of that by 24 degrees. Therefore, the bearing is 270 degrees minus 24 degrees, and that is 246 degrees. Here we have a particular matrix of transformation, and we have points that the matrix would have transformed into their images as we have them right here. The matrix of transformation will multiply by the position vector of the points, resulting in their images. This may be written in a single matrix equation. So this is our matrix of transformation, multiplying 3, 5 written in column form, 7, 2 in column form, and the result is 5, -3, the image of V, and 2, -7, the image of W. This is a matrix equation that we may solve by eliminating this matrix from the left-hand side. In solving the equation, the inverse of the known matrix on the left-hand side will multiply the other matrix that is on the right-hand side. So take this matrix and multiply by its inverse on the right-hand side, and this is what we get. In order to form the inverse of this matrix, we need to find the determinant. 3 times 2 here, 7 times 5 here, and then what we have here is the adjoint of this one that is formed by changing the position of these two and changing the signs of these two. There. Now, after multiplication or simplifying this matrix product, the result will be the matrix ABCD. Matrix multiplication is not commutative. The matrix is the second in the product on the left-hand side. Its inverse has to be the second in the product on the right-hand side. So we have this first. The matrix that we are eliminating is the second one. When we multiply by the inverse on the right-hand side, the inverse of this matrix will have to be the second one on the right-hand side. Of course, as usual, multiplying row by column. 5, 2. 5, 2, 2, negative 5. 5, 2, 2, negative 5. Then we have 5, negative 7, 2, 3. 5, negative 7, 2, 3. Then this row by this column, the lower by the left, the answer goes to the lower left. So negative 3 times 2, negative 7 multiplied by negative 5, the lower with the left, the answer goes to the lower left. And what do we imagine? The lower with the right, the answer goes to the lower right. Negative 3, negative 7, negative 7, 3. And what do we know? 5, 2 is 10, minus 10 is 0. 5 multiplied by negative 7, negative 35, plus 6. That's a negative 29. And we have here negative 6 plus 35, that is a positive 29. 35, 21 minus 21 is also 0. No problem. 1/29th, well, a negative 1/29th, and then we have negative 29, negative 29. So we are sure that those fractions will be reduced to give 1. In this case, we have a negative with a negative, that's positive. And in this case, we have a positive with a negative, that will be negative. So A is 0, B is positive 1, C is negative 1, and D is 0. It is not enough to write the answer in a single matrix. There is no doubt that we will make use of such a form, but the statement of the problem required that we determine the values of A, B, C, and D. And that we have done right there. Let us make an analogy as far as possible between solving a linear equation and solving a matrix equation. And I'm saying as far as possible because we all know that in analogies we have similarities that may be used to our advantage, and we have differences that we need to consider. So that's our matrix form, and that is our linear form. In order to find x, we need to eliminate m on the left hand side, and that is pertaining to the matrix, and l on the other hand, that is pertaining to the single linear equation. We can divide n by l, but we cannot divide by a matrix. We cannot divide by m. We have to multiply by the inverse of the matrix. That's how we divide, or the equivalent of division of matrix. We multiply by the inverse of the matrix, like so. And we are dividing by L for the other one. Notice that on the left hand side, m precedes x. And on the right hand side, m inverse precedes n. So m precedes x here, and m inverse precedes n. That is how we have it. We always do it and take it for granted, but we have a very good reason for doing it. The fact that matrix multiplication is not commutative means that if m precedes x on the left hand side, its inverse needs to precede n on the left hand side. What I'm saying is that we know that in multiplying matrices, the order of the matrices matter. And when we say order, we mean 2 by 2, 2 by 1, etc. So the order of the matrices matter. So we are sure that we can only, for a matrix 2 by 2 to be multiplied by a matrix that is 2 by 1, we know that the 2 by 2 has to go or precede the 2 by 1. Right? So we take that for granted. The 2 by 2 must precede the 2 by 1. However, we also need to be mindful of the fact that matrix multiplication is not commutative. In this particular case, we do not have any 2 by 1s. We have 2 by 2s. However, it is still very important that we are careful where we place the inverse of the matrix, whether it precedes or comes after the one that we are multiplying by. Because matrix multiplication is not commutative, therefore, if M precedes what we have representing the matrix, which is X, on the left hand side, its inverse must precede N on the right hand side, because multiplication of matrices is not commutative. Therefore, although we have 2 by 2 matrices and we may multiply in any order, it is possible we need to be mindful of the fact that matrix multiplication is not commutative. Dividing by a number is the same as multiplying by its reciprocal. In the case of the linear equation, it does not matter if 1 over L precedes or comes after N. So it does not matter if we put 1 over L here or 1 over L on the other side. It does not matter how we do it, because we are talking about a linear equation. But when we are talking about matrices, it does matter. The problem on the previous slide made use of 2 by 2 matrices. This eliminates the restriction encountered when multiplying a 2 by 2 matrix by a 2 by 1 matrix. However, matrix multiplication is not commutative. Now, what I'm saying is that if we are multiplying a 2 by 2 by a 2 by 1, because of the order 2, 2, 2, 1, because of the order of the matrices, the 2 by 2 must precede the 2 by 1. The problem that we have does not make use of a 2 by 1. It makes use of 2 by 2s. But it matters where we put the inverse of the other matrix. We need to put it in the same way that we have on the left hand side, because matrix multiplication is not commutative. On the left hand side, the matrix that we are eliminating comes after the matrix that we are attempting to find. See? Right there. This is the matrix that we are attempting to find. The matrix that we are eliminating comes after. Its inverse also has to come after the matrix on the right hand side. The reciprocal of the determinant of the matrix whose inverse we are attempting to find precedes the matrices. Notice that although what we have here, these two matrices are placed or comes after the matrix in every single case, but we did not put 1 over the reciprocal down here. The reciprocal of the determinant of the matrix whose inverse we are attempting to find precedes the matrices. Its position is not critical because it turns out to be a pure number, which is a scalar. Its multiplication is commutative. So multiplication by a scalar is commutative, and this may be placed anywhere, but we cannot do that with the matrices. We may therefore use our principle and arrive at a little rule. If the matrix that we are eliminating precedes the other matrix on the left hand side, then on eliminating it, its inverse must precede the other matrix on the right hand side. The converse is also true. Namely, if the matrix that we are attempting to eliminate follows the other matrix on the left hand side, Then on eliminating it, its inverse must follow the other matrix on the right hand side. We have the image of Z as Z prime, which is 5, 1. Those are the coordinates of Z prime. We are required to state the coordinates of Z. Therefore, there should be a way to arrive at Z just by observation. In the process of transformation that we have here, we observe that the ordinates in a given point exchange places, and there is a change in sign in the one that was initially the x ordinate. So we have right here 3, 5 going to 5, negative 3. We realize that the values exchange places, and we have a change in the sign of the one that was initially the x ordinate. And we have the same thing down here. In order to determine the coordinates of Z, we reverse the process by carrying out the reverse of each step, performed in the reverse order. What are the steps? Exchange places. That is step 1. Step 2 is what? Change the sign of the one that was initially the x ordinate. How do we do that now? We will change the order here. Let's go straight ahead. Change the sign of the one that was initially the x ordinate. And then what do we do next? Then we exchange places. So we exchange places, then change the sign of the one that was initially the x ordinate. Now we will what? Change the sign of the one that was initially the x ordinate, and then we exchange places, and that will return the point to its original. And there is Z prime. What do we do first? Change the sign of the one that was initially the x ordinate. The one that was initially the x ordinate, this one. Change the sign of that one. And then what do we do next? Exchange places. And there we have our original point, Z. There are some candidates who are aware of the fact that if we have a matrix M that transforms a point A to its image A prime, then the matrix M inverse will transform the point A prime to A. The matrix of transformation is responsible for the reverse process. So what we do is, if we have M transforming A to A prime, then M inverse will transform the point A prime to A. So what do we do? If we are attempting to find Z, if we have Z prime, we'll take Z prime and multiply it by the inverse of the matrix of transformation, and we will result in Z. Students know that. Because of this, they would have opted to take the matrix of transformation that we have just found, find its inverse, and use it to multiply the point Z prime. So there we have the A, B, C, and D that we found, and we just put them in their respective places inside of the matrix M, and that will be the matrix of transformation. Find the inverse of the matrix M. 1 over the determinant 0 multiplied by 0 minus 1 multiplied by negative 1. That's what we have. Exchange the places of these two and change the sign of these two. That is what we'll have. Simplify. We have M inverse is 0, negative 1, 1, 0. So this they will take, which is the inverse, and they multiply that by the image of the point Z, which is Z prime. Now use it to multiply the point Z prime. And if we do that, we have 0 multiplied by 5 then negative 1 multiplied by 1, negative 1. Then we have 1 times 5 is 5, and 0 multiplied by 1 is 0. So we'll have 5 right there. Rewrite the point Z in coordinate form. Do not forget that when we are asked for a point or for coordinates, we do not just solve the problem, but we write the answer in the required form. So Z is negative 1, 5. And that we have done by finding the inverse of the matrix of transformation and use it to multiply the image. And that results in the original point, which is a lot of work, to say the least. Candidates have to get accustomed to using the method that the examiners suggest in solving problems. When the instruction is write down or state, candidates may just use common sense and just write the answer down rather than going through this process. Neglecting the simple instruction may result in wasting time and probably attempting to use a method that one is not familiar with. So we may use a method that we are not familiar with if we would have gone through this. Probably we are familiar with this method, but to go through all of this when we should be able to just look at the answer, look at the information that we have there and write the answer down, then we know that is a little bit too much. My student Brittany Brown can tell from memory which transformation that matrix represents, but I can't. I have to work it out. In forming the matrix of transformation, the point 1, 0 and the point 0, 1 are written as the two columns of a 2 by 2 matrix and subject to the transformation. The resulting matrix is the matrix of transformation. Take the point 1, 0 and take the point 0, 1 and write them as two columns of a 2 by 2 matrix. Then subject each one to the transformation. 1, 0 will go to 0 minus 1. Like that. So this is 1, 0, this is 0, negative 1. So 1, 0 will go to 0, negative 1. And what about 0, 1? 0, 1 will go to 1, 0. Also, the point 0, 1 goes to its image 1, 0. Like so. Which transformation is responsible for that? Let us cause the transformation to be more true to life. Let us take a second look at it and see. Right. Notice that what? 1, 0 goes to 0, negative 1 and 0, 1 goes to 1, 0. What is happening right there? It's so obvious. That's a rotation. Right. The transformation is a rotation by 90 degrees clockwise about the origin. How can you miss it? Some candidates, some of my students, they know these from memory, but I do not bother to commit things to memory that I can work out quite easily. As a matter of fact, I don't do them, or I don't use them quite often, so it is not necessary to always have them in my mind. There we have a point P, 2, 7, and a vector PR, which is 4, negative 3. OP is the position vector of the point P. Now the position vector of a point is the vector that goes from the origin to that point. And all we need to do is write the coordinates of the point in the form of a column vector. That's all there is to it. Or a column matrix that turns out to be a vector. That's all there is to it. Now we need to find OR. we have PR and we need to find OR. Good that we have the vector OP. We need to find OR. We will make use of PR and OP by triangular law. So PR is equal to OR minus OP by the triangular law. And let us transpose that in order to find what do we need to find? We need to find OR. So OR will be made the subject of the formula by transposing this to the left-hand side. By so doing, we will have this being a positive. So we have OR is equal to PR plus OP. And we add those two vectors and the result is 6, 4. So we have OR is 6, 4. Use the triangular law and transpose. S is 14, negative 2, and we need to find the vector RS, and we will use again the triangular law. S is 14, negative 2. So what do we know? RS is equal to OS minus OR. RS is equal to OS minus OR. We have OR here and we have OS can be determined by using its coordinates. So there we have RS is equal to 14, negative 2 minus 6, 4. That turns out to be 8, negative 6. So we have RS is 8, negative 6, and we have PR is 4, negative 3. As we can see, the vector RS is twice the vector PR. If one vector is a multiple of the other, then they are parallel. This follows that P, R, and S are collinear.